All right, we're ready to start part two of our hydronic applications course. Good morning, John.
Good morning, Mike.
Hopefully everybody had a very good weekend, and hopefully everybody enjoyed part one. So far, John, the feedback has been very good. Just wanted to do a couple of housekeeping items right off the bat. So this is part two, domestic hot water preheating using external heat exchangers. We have two more sessions that are going to be occurring every Monday at 8 a.m. until we're complete. If you do not want to use computer audio, you'll notice on the screen here we have a dial-in audio number as well as an access code for anybody who is having trouble hearing us or wants to just use their phone versus their computer. A little bit of background on Eden Energy. We were founded in 1981. We focus on a variety of different specialty markets. We're fortunate that our sponsors that are shown on the screen have participated to make this training a go. So you have IBC, one of the leading boiler manufacturers in North America. You have Rayhow, which is a leading manufacturer in PEX, water furnace geothermal heat pumps, Velo for their pumps and circulators, FlexCon for their expansion tanks and their new buffer tanks, which John and I are going to talk about a little bit today. And of course, we all know Colefi. If you need last week's handouts or the slides for last week, just let us know. If you have questions that come up during training, just let us know.
Okay.
All right,
we also
hand it over to you.
Okay. Well, thanks, Mike, and good morning, folks. We appreciate you getting up, starting your work week with us, and we're delighted with the turnout that we had last week, the interest we've had, and also looks like we're doing very well here today. So just want to reiterate what Mike said. If you didn't see last week's intro to this system, you can go to YouTube and just go to Eden Energy Equipment on YouTube, and you can get that. And also there's a PDF of all the slides. Now, if by chance you weren't with us last week, you see the schematic up on the screen. This is a system that we analyzed last week. It looks pretty complicated. It does involve two different heat pumps. We have a geothermal water-to-water heat pump. We have an air-to-water heat pump. We do have one of the new FlexCon Argosy 119-gallon buffer tanks. Both heat pumps basically maintain the temperature of that buffer tank, and we have several different loads going from that. We have slab heating in a basement. We actually have slab heating in a garage, but we're separating that with a heat exchanger so we can do an antifreeze solution in the garage. And then in the upper right here, you'll see a collection of panel radiators and radiant floor circuits. So how do you keep all this organized? It's actually, it's kind of a testimony to the flexibility, versatility of hydronics, that we can put systems like this together to allow them to be very customized to the client requirements in the project. So what we're going to do this week, we're going to focus in on a specific detail that we used in that system, and it's a method for preheating domestic hot water using energy that has been put into a buffer tank, really from just about any kind of a heat source. We in the system that was constructed and we just looked at, we used heat pumps as the primary heat source, but it could be a boiler, it could be solar collectors, it could be just about, it could be a pellet boiler, anything that can heat up that buffer tank. So we're going to focus in on that detail. This is actually a detail that is used quite a bit in the European market. It's not a common detail in the North American market at this point, but it does have some redeeming qualities that we'll get into. Okay, so methods for domestic water heating. We're going to look at 4 different approaches to taking energy from a buffer tank and transferring that energy into domestic water. And 3 out of these 4 can be used with either boilers or heat pumps. And so we've got a Modcon boiler there. We've got a water-to-water heat pump, And over on the far right, we're looking at an air-to-water monoblock style heat pump. So what are those four methods? Well, the first one applies just to heat pumps, and it's something called a de-superheater. Some of you, I'm sure, are familiar with it, but a de-superheater is an extra refrigerant to water heat exchanger. It takes the hot gas directly from the discharge on the compressor and takes some of that energy that is necessary to cool the refrigerant from a superheated vapor back down towards a saturated state before it goes into the condenser. And it uses that energy to heat domestic water. And today there's a variety of heat pumps available, many geothermal heat pumps, whether they be water to air or water to water, do have the option for a de-superheater. And then we're going to look at two different types of indirect tanks. And I'm sure many of you are familiar with the concept of an indirect tank, where we have a coil, usually in the lower portion of a tank, and we're going to send hot water from a heat source, usually it's a boiler, through that coil, and we're going to transfer heat from the coil to domestic water in the tank. And then another variation on indirect water heaters is it's come to be known as a reverse indirect. So all it does is it swaps the domestic water in the tank on a standard indirect. In a reverse indirect, that domestic water will be in a coil suspended within the tank, and then the heat source water will be surrounding that coil. That's a reverse indirect. And then finally, the detail we really want to focus on more is what's called an on-demand external heat exchanger. Instead of having domestic water heated within the tank, we're going to heat it external to the tank with a stainless steel brace plate heat exchanger. So let's start in with a schematic here and a de-superheater. This happens to show a split system air to water heat pump. So we have our outdoor unit. Here's an example, a Nordic outdoor unit. And we have refrigerant line sets that come in to the indoor portion of the system. And you can see that down here. And you'll see there's a couple large pipes here. They look to be maybe inch and a quarter size pipe. Those are the pipes that go off to the heating system. And then you'll see the two smaller pipes here. That's your indicator that that unit has a de-superheater in it. And if we look at it schematically up here, we take the hot gas coming off the compressor, it's going to go right through that little heat exchanger. And at the same time, there's a small stainless steel, in some cases it's a bronze circulator, but it's rated for potable water. And that is going to take water from the lower portion of the electric water heater, the cooler water in that tank, and it's going to circulate it and counterflow through that heat exchanger and send it back, usually into the dip tube of the tank. And you'll notice the tank still has heating elements in it. So the heating elements are going to be there to top off that temperature if necessary. Now, some of the modern de-superheaters can actually go up to about 130 degrees water temperature, and some heat pumps today will have safety limits that if the domestic water temperature leaving the de-superheater exceeds 130, it'll actually turn off the circulator, and that's purely a safety device so that you don't create scalding hot water. So depending on how much load is on that heat pump, how much it's running, whenever that heat pump is running, whether it's running in heating mode or running in cooling mode, that de-superheater is taking roughly about 10% of the energy that the heat pump has and transferring it over into that domestic water. In cooling mode, the advantage of a de-superheater is really nice. You're taking heat that otherwise would be rejected outside, either to outside air in the case of an air to water heat pump, or into an earth loop in a geothermal system. You're taking that heat and you're actually using it to heat domestic hot water. So you're getting, in effect, free domestic water heating at that point. Now, some designers and some installers will use a single tank system like this. Down in the lower right corner, you see a double tank system. And what that does is it will bring up the performance of the heat pump, because the heat pump is operating on cooler water. The preheat tank temperatures are typically that's where the cold water enters the system, and then the preheated water would feed into the dip tube on the backup electric water heater. I'm kind of torn on this. It in theory, if you're using a fair amount of hot water, it probably makes sense to have a preheating tank. If you're not using a fair amount of hot water, I don't really see the advantage of that, considering that you've got not only the expanse and the space requirement of the second tank, but you also have more standby loss from the system. So that's the basic idea with an air to water heat pump and a de-superheater. Now, it's the same idea with a water to water heat pump. So I'm just breaking out what we had last week. The earth loop supplies energy to the heat pump, and you'll see over here within the heat pump that small heat exchanger with a stainless pump that goes up to the domestic water tank. Many of the heat pump manufacturers offer it as an option, so you can order the heat pump with it or without it. I think it makes sense in most cases to order it with it, unless that heat pump is strictly going to be applied to a space heating load. Okay.
John, on that note, there's actually a question about domestic hot water. So Dave is asking roughly what is the cost of a superheater? So in Ontario, you'd be looking at somewhere in like the $400 to $550 for the superheater add-on.
Okay. Okay. Now, another approach, and again, this can be applied with either type of heat pump or with a boiler, is an indirect, well, what I'll call an indirect with a large, and I want to stress, large internal coil. We look over here in the schematic. You want to keep in mind that many indirect tanks in the North American market were created with the assumption that a boiler can operate at temperatures in the range of perhaps 180 to 200 degrees Fahrenheit. Even a Modcon boiler under a call for domestic water would leave its normal reset control schedule and go to these high water temperatures. And of course, the high water temperatures get you a higher rate of heat transfer, which allows a smaller coil to transfer, an adequate amount of heat. Well, I do see potential problems with taking that type of a tank and putting it on a heat pump, simply because these heat pumps do not produce these high water temperatures. And even heat pumps that can press up into that 140, 150 degree range, the COPs are not great under those conditions. So the solution for something like this is to have a larger internal coil. And you'll see a lot of tanks in the European market that have a much larger internal coil in terms of surface area. I just showed an example over there on the left of one tank that is available in North America that you can order with a fairly large internal coil. And again, the critical thing here is to make sure that the heat transfer through that coil does not become a bottleneck to the overall heat transfer from the heat pump to the domestic water. If the coil is too small inside that indirect, what's going to happen is the heat pump temperature is going to continue to go up. The condenser pressure and temperature will increase. And at some point, that heat pump is going to shut itself off based on either a discharge pressure limit or a temperature limit. And you'll probably have to go down, press a button to reset it. And the reason that's occurring is, let's say the heat pump is putting out, I'm just picking a number, 40,000 BTUs per hour, but at 120 or even 130 degree Fahrenheit, the coil in the tank can only dissipate, let's say, 25,000 BTUs per hour into the water in the tank. Remember, the water in the tank isn't all cold water. It's water that's been heated. So we have natural convection heat transfer, which is not nearly as productive in terms of heat transfer as compared to forced convection heat transfer. So if we're putting out 40 at the heat pump, but we're only sinking 25 into the tank, the other 15,000 basically just accumulates in a small amount of water between the condenser in the heat pump and the coil in the tank. And eventually, as I said, the heat pump will shut itself off. So if you are going to use a indirect tank with a heat pump, make sure you get a tank that has a large internal coil. And I would also recommend that you compare the heating capacity of the heat pump against the heat dissipation ability of that coil at a temperature of around 120, maybe 125 degrees, to make sure you've got a reasonable balance, that you're not going to drive that temperature too high. Okay. Now, I mentioned the reverse indirect, and Turbomax has been a long-standing manufacturer of this type of a tank, Canadian manufacturer. And you'll see in the cutaway down there in the lower left, what's inside a Turbomax tank is a steel shell, a pressurized steel shell that holds water from the heat source. So the majority of the volume of that reverse indirect tank is not potable water. It is what I'd call system water or heat source water. And then you have multiple copper coils suspended within that tank, and the domestic water flows through the copper coils. It goes in at the bottom, you can see in the schematic over here, and as it's drawn from a fixture or multiple fixtures, it passes up through these internal coils. And I'm showing the possibility of a tankless electric water heater. Two functions of that. Depending on how warm we keep the buffer tank, we may need to do what I call a temperature top off on the domestic water. Let's say, for example, the buffer tank is at 90 degrees, which might be sufficient for space heating on a fall day or a spring day with, let's say, a radiant floor heating system. But we don't want to send 90-degree water to our taps. We want it at let's say 120 or perhaps even higher. Well, the preheated water comes out of the coils and it passes into a thermostatically controlled tankless water heater. And the new versions of these tankless water heaters are intelligent. They understand what the set point is relative to what's coming in, and they actually change the current that flows through the heating element to apply the necessary power to bring that water from its preheated temperature up to whatever the set point is. And then that water goes out. I would always recommend an ASSE 1017 anti-scald valve in there. It's a safety device. It's a guard against a scalding high temperature. If for some reason the thermostat in the tankless water heater failed, and there are safety lockouts within the tankless water heater as well, but worst case scenario, you have a failure of safety controls. That is the last guard of against scalding hot water. Just a couple details on this too. Notice I've put a couple valves here, which I call isolation flushing valves. The idea here is that we could isolate that tankless water heater, and then we could connect a couple hoses, double-ended hoses, to those hose bibs, and we can actually flush some type of a mild, like a citric acid. There's another acid that's used, but it's not a highly aggressive acid, but it's used to basically counteract the buildup of lime scale inside the water heater. And there are manufacturers that have kits available today. It's a small sump pump, a 5-gallon bucket, and some of this mild acid. And the idea is that you circulate it for a period of time through the tankless water heater, and periodically you do an internal cleaning to make sure that you aren't accumulating scale. The rest of it's pretty straightforward. You see there's a circulator here that goes out to a zone distribution system. So the nice thing about this approach is that this tank is serving both as a buffer for the space heating loads, as well as a temperature, or a preheating tank for domestic hot water. Now we're going to talk about how hot should that tank be. Some of you are probably thinking right now, well, should I keep that tank at 125 degrees and get most of my heating from a single pass going through there? Well, you could do that, but keep in mind that is going to penalize the performance of the heat pump, because we're going to force the heat pump to operate at temperatures that are pretty close to its upper limit. That's going to bring that COP down. The other thought would be, well, maybe I'll keep the water temperature down in the tank, which will improve the performance of the heat pump, but it also means I'm going to have to do a greater temperature lift from my preheated water to my final delivery. And I'll show you some models that we've put together to try to answer that question for you.
John, there's a
This
couple
is
of
just,
questions that
okay,
have
go
come
ahead, Mike.
in relation to that last slide.
Yep.
So Daniel actually asked the question, what do we recommend for sizing the internal coils as a rule of thumb when you're doing it for a heat pump? He also asked, what tanks available in North America do you know meet heat pump requirements? Daniel, the Turbomax, and so we're the water furnace distributor for Ontario, but the only tank we would put on a heat pump would be the Turbomax because of the reason that John alluded to. There are other manufacturers that do have much larger coils inside of them. IBC, for one, recently redesigned their indirects, have a much larger coil in some of them. Can you think, John, of other manufacturers that would be usable? And what is your rule of thumb if you have one?
I don't have a rule of thumb because typically you don't have control over that coil. That's going to be a decision the manufacturer makes. I can tell you from purely an engineering standpoint, the bigger the coil, the biggest coil you can afford. How's that for an answer? The biggest coil you can afford, because the greater the surface area, the smaller the temperature difference between the water in the tank and the leaving water temperature from that coil. So in general, the manufacturer is going to determine that coil surface area. The two things that I would check on with that, I would look at a water temperature, I would say coming from the heat pump, or a tank temperature no higher than 120 degrees Fahrenheit. Can the tank dissipate the full output of the heat source into the water using that as the shell temperature of the tank? Again, the thing you're trying to stay away from is that, what I call that heat transfer bottleneck. You don't want a situation where the coils in the tank, whether it's a standard indirect or a reverse indirect, you don't want a situation where those coils cannot dissipate heat at the same rate that the heat source can put it out, because that's going to drive that temperature in the heat pump water circuit. It's going to drive it up, and that heat pump's going to lock itself out based on probably a high condenser pressure situation.
And one last question, John, before we move on from here. Jeff was just asking a question. He was under the impression that in reverse indirects normally required storage water at 180 degrees plus.
No. You can get data from the manufacturer that will show what your first hour rates are, first hour hot water delivery rates over a range of water temperatures. Now, one of the classic applications for these reverse indirects has been in in a large custom house where you've got 10 different bathrooms, you've got high-end showers. We've done projects like that, and you can have domestic water demands of upwards of 20 gallons a minute. And if you do the math on that, you're closing in on 1 million BTUs per hour of heat transfer rate to provide 20 gallons a minute from, say, 45 or 50 degrees Fahrenheit up to 120. And these tanks operated at high temperatures where you might have a multiple boiler system. It's actually a really nice application. 2 or 3 boilers all at full, I call it full afterburner. You've got your maximum boiler output, and you're dumping it all into this tank. The Turbomax can accept, I believe I remember the large Turbomax, the 119, can accept on the order of 1 million BTUs per hour of heat input under those conditions, with that shell at maybe 180 degrees, 190 degrees. But the same tank operated at lower temperatures is definitely going to have a lower rate of heat transfer, but that heat transfer rate could be adequate for a more normal residential application. Okay, now just to show one other variation, this is another product from Canada from a company called Thermatlantic over in Maritimes. The slight variation is, instead of internal coils, they have a 40-gallon stainless steel inner tank that is supported within the outer tank shell. And you see that the idea is pretty much the same. The cold water would come down into that stainless steel tank and simply be immersed. That tank, that inner tank, is immersed in the outer tank. So again, you have natural convection heat transfer across the wall of that tank. And depending on the temperature of the buffer tank and the rate of domestic water usage, you could be pretty close to the upper tank temperature as you leave. And if you do need a boost, again, I'm showing the exact same system here, a tankless electric water heater to do the boosting. So it's just another product option with a slight variation. Instead of coils, it uses this stainless steel inner tank. Now, just to point out, those details are not just relevant to heat pumps. They can be applied to Modcon boilers. Now, obviously the efficiency of the Modcon boiler is going to be higher if we can keep the water temperature lower. So yes, these boilers are capable of going to the 180-degree range, but they are not going to be quite as efficient as they would be if they were in maybe the 130 or 140-degree range. So again, the benefit of using any type of indirect tank with a large internal coil or this stainless steel inner tank is that we can get adequate rates of heat transfer without forcing the boiler to go up into a non-condensing mode of operation. So we gain in terms of efficiency. So anytime you're dealing with heat exchange in a hydronic system, the bigger the heat exchanger, the better things are from an efficiency standpoint. It's really a matter of, as I said earlier, it's a matter of what can you afford. The bigger, the better as far as heat transfer area. So we're going to stop. We're going to do, I'll read this poll question, and then Mike is going to tally up the responses. How often do you use an electric tankless water heater in a residential application? And you've got 50% or more of my systems, less than 25%. Only if your customer asks for it or you never use it. So take a minute and just reply to that poll, and we'll see, kind of gauge it. I suspect that electric tankless water heaters are probably not as common as other types of tankless water heaters at this point in the market.
Yeah, it'll be an interesting poll, John. I tend to agree with you. We're at almost 70% of people have voted, so I'll give it a few more seconds.
Okay.
And, we'll see where we're at. So here's the results of the poll. So at this point, we have 1% of voters saying 50% or more of my systems. 7% are saying 25 to 50% of my systems. 41% are only if customers ask for it. And as I suspected, 51% are never.
Never. Okay. Well, it's not surprising, but I will comment that as we move towards more electrification in systems, you are going to have customers that want to build all electric houses. And I suspect that natural gas service is certainly well established in the Canadian market. But as the trending will move towards all electric houses, it's a product that you should at least be familiar with. There are several good products on the market now that use solid state controls, very accurate in terms of water temperature control. They're small and they're relatively, they're affordable. They're not they're certainly not as expensive as an instantaneous gas-fired water heater because they're a lot simpler, a lot smaller. So it's a product that if you've never used it, I would just suggest take a look around, see what's available, and you may take an interest in it. Okay, now, so we've talked about de-superheaters. We've talked about two different types of indirects. This is another detail that can work quite well for domestic water heating, and it's an external heat exchanger. And let me start over on the right over here with this schematic in the upper right corner. We've got our buffer tank. The water in that buffer tank is what I'll call space heating water or system water. It's not potable water. And to the right of the tank, we've got a stainless steel brace plate heat exchanger like the one you see in this photograph over here on the left. So I'm sure most of you can figure out how this works. The circulator, when it's running, would take warm water from the top of the buffer tank. it would pass it down through the, what I'll call the primary side of that heat exchanger, goes through a check valve. Make sure you have that check valve either there or built into this circulator, and then it goes right back into the bottom of the buffer tank. So we're sending heated water through the primary side, and at the same time we have cold domestic water coming in through a flow switch. We're actually using the flow switch through a relay to turn on this circulator. And I'll talk about that more in just a moment, but the cold domestic water goes in. Notice it goes in counterflow, so we get the highest log mean temperature difference across the heat exchanger. And that's our preheating effect right there. Out of there, we go into either a tankless electric water heater for a temperature boost, or down here in the lower right, we go out of our heat exchanger into perhaps a 30-gallon or 40-gallon tank. So we're getting what we can get as a preheat through that heat exchanger, and then we're using some type of auxiliary to top it off, okay? And I will mention, if you do this with a boiler, you probably can keep the buffer tank at a temperature where conceivably you could eliminate the need to have the tankless electric water heater or the tank type water heater. The heat exchanger sizing would be the critical thing. Now, here's the heat exchanger, and just to give you an idea, this is a 5-inch wide, 12-inch tall, 40 plate deep. Okay, it's roughly about 4 inches of stainless steel plates there. It's made out of 3/16 stainless steel, and the piping you see here, this 1-inch piping coming in, is from the top of the buffer. This is one of the FlexCon Argosy tanks, and it comes down, the flow comes down through the primary side of the heat exchanger, back down circulator, and right back into the tank. The other two pipes are just potable water, cold water coming in and preheated water going out. And you can see these two valves that are here. These are the isolation and flushing valves. These allow you to isolate the potable side of the heat exchanger and connect up those hose bibs and do a mild acid flush if you need to. Now, one of the things that is new, I'm sure to many of you, is the flow switch. Flow switches have been around on the market, and they're used for different things. In larger capacity systems, flow switches are used to verify a flow before, for example, a compressor can start. Most air-to-water heat pumps today have built-in flow switches. So if the circulator fails, you don't just run the refrigeration system and superheat the refrigerant. They want to have verification of flow before they actually will allow the compressor to turn on. Now, the flow switches we're talking about here are small. Here's a photo of what they look like as one example. These are built by a company in California by the name of Harwell. I don't know the exact price. They're fairly inexpensive. They're probably $35 to $40. And it's a very simple device. It's basically a body that screws into a 3/4, in this case, a 3/4 inch stainless steel T. And there's a paddle with a magnet on it. And these paddles are calibrated. This particular flow switch will turn on when the domestic water flow, this would be ultimate domestic hot water, gets up to 0.7 of a gallon per minute. And once it closes, there's a hysteresis, and it opens when the flow drops down to 0.4 gallons per minute. And all that happens is the paddle and the magnet get pushed by the flow, or the drag of the flow pushes it, and there's a reed switch in there, a very small switch that activates. And you'll see you can order these with different types of cabling or contacts on them. One of the things that I feel is important, even though these switches technically have a line voltage rating, I would not suggest going directly from the flow switch to a circulator. You can see that the wiring really isn't code acceptable for line voltage. So go to a relay. What we did in the system we talked about last week, we went right to one of the zone outputs in a multi-zone relay center. Just treat the flow switch as a thermostat, and the line voltage output associated with that zone in the controller just turns on that circulator. So the sequence events would be simple. You would you would open up a faucet. Let's say you want to take a shower. You open up a faucet, and instantaneously that flow, well, I'll say within a second, a shower head would quickly get above 0.7 gallons per minute. The circulator would turn on. Circulator would spin up, another second. It would be running. And notice that that heat exchanger is close to the buffer tank. You can see it here. It's right next to the buffer tank. We're trying to minimize the piping distance and volume between the buffer tank and the primary side of that heat exchanger. So I would say within 2 to 3 seconds of opening that faucet, this subassembly for preheating domestic water is active. The circulator is on, and you have warm water from the buffer tank going through the primary side of the circulator. Now, sizing that circulator, same thing. The bigger that, sizing the heat exchanger. The bigger the heat exchanger, the better. Well, I'll show you an example of a software. Several companies that sell brace plate heat exchangers have software that can size these up. And my suggestion to you is to pick a heat exchanger so that the difference between the incoming water from the buffer tank and the preheated temperature leaving the heat exchanger is no more than 5 degrees. That temperature difference is called the approach temperature difference. In theory, an infinite heat exchanger would have a 0-degree approach temperature difference. So the water leaving the heat exchanger would be exactly the same temperature as the water coming in. We don't have infinite heat exchangers. So when you size it, be generous, because again, you're going to get a higher temperature lift on the preheating function if you use a larger heat exchanger, okay? And keep that approach temperature difference no higher than 5 degrees. Now, let's go back here. Just a few more details. The system we did actually at my daughter's house, we did not use it. We used a standard 38-gallon tank type water heater. It had a 4.5 kW element. We used it because we could tuck it right in under a stair landing. So it's a low profile tank. It's actually in a secondary drain pan, okay? And there's the flow switch right there. Now the flow switch is actually on the cold water. Actually, I misspoke. Normally we'd put it on the cold water line. It actually is on the preheat line between the heat exchanger and the tank. And I think that was done just because of where things were located in this system. But I also want to call your attention, we do have a ASSE 1017 anti-scald valve on that as well. So, there's the sub-assembly, hot water from the tank through the heat exchanger, circulator with a check valve. We do have a purge valve there back into the tank. I mentioned the importance of a check valve, either built into the circulator or a separate check valve. Without that check valve, what could happen is, remember, we have space heating zones out here. If we have flow going out here and it's coming back, we don't want any of that return flow to go backwards up through that heat exchanger and short circuit the tank. So that's why we need that check valve in there, okay? Now, this is a slide I showed last week where we're talking about performance of the air to water heat pump. This was a Space Pack 5-ton split system, low ambient heat pump. And, one of the things about spreadsheets, anytime somebody shows you a spreadsheet, they're very proud of the spreadsheet, as I am, because there's a lot of information built behind the scenes in that spreadsheet. There's very detailed models for the capacity and the coefficient of performance of the heat pump. There's weather data built in and so forth. Well, I'm going to cut to the quick. What we did is we wanted to determine seasonal average coefficient of performance based on different water temperatures in that buffer tank. So we ran a model, and we did limit the simulated COP to nothing higher than 4.5, and the simulated heating capacity nothing higher than 68,000, even though the manufacturer's curves would imply that those numbers could be a little bit higher, okay? So we want to be careful on those outer ranges anytime we model, that we don't create what I'd consider unrealistic conditions. So if we maintain the buffer between 100 and 110, and the idea would be when the tank temperature sensor drops to 100, we turn the heat pump on. And when the tank temperature sensor gets to 110, we turn the heat pump off. So we're averaging 105, and you can see that's what our numbers are right here, averaging 105. Our seasonal COP was 2.75, which is pretty good. This is in a cold climate. It's almost 8,000 degree days. Now, if we lowered that buffer tank temperature by just 5 degrees, so we turn on at 95, we turn off at 105, our COP jumps up to about 2.9. So right away, you can see that that heat pump performance is quite sensitive to that condenser water temperature. The lower we can keep it, the better. The final scenario we modeled was full outdoor reset control. So instead of having 105 degree water as our average tank temperature, there's actually an equation that would calculate based on outdoor reset what that tank temperature needs to be. And you can see a substantial jump in seasonal COP up to about almost 3.5. So over on the right, we compared the temperature, we compared energy prices. This would be in upstate New York, spring of this year. We're paying almost $2.50 for a gallon of propane, so it works out to about $29 per million BTUs delivered. Fuel oil works out to about $18.50 per million. Our electricity at that point was about 9 cents a kilowatt hour, and with the COP averaging 2.75 over the heating season, we're under $10 per million. So we're actually significantly less expensive to provide thermal energy with that heat pump than we are compared to propane or fuel oil. Now, this house is in a rural area. It does not have natural gas service. I did not compare it for that. Now, if we could operate the heat pump on outdoor reset control, where we're getting almost 3.5 for a seasonal average COP, we're dropping to less than $8 per million. So in this particular scenario, you can see the energy from that heat pump is very competitively priced against the fossil fuel options.
John, just want to point out before we move further. So for those noting that John's using American numbers, there's two handouts I've attached. One is called the Canadian Field Study of Ground Source. So that's where the gas company did a study comparing heat pumps to natural gas. So part one we gave out last week, which is the cooling data. This week is the heating data. There's also a domestic hot water study. This one is American on heat pump operation, which is also a good read. A couple quick questions, John, I just want to address before we go too much further along. One was pretty easy, was which flow switch do you actually recommend? Like, is there a particular brand that you like?
Yeah, we've used a Harwell switches. If you Google, it's Harwil, Harwell, and they make a wide range of flow switch products from very small residential, like OEM type flow switches that you would find being used in some of these tankless water heaters, right up through industrial size switches. They have all types of mounting and enclosures. So Harwell out of California is a good one.
Okay, and then one more.
And as I say, fairly inexpensive.
Perfect. So the other one that's shown up a lot, I've probably had a half a dozen people ask this question. So in different jurisdictions, there's a requirement to store the water at a temperature where it won't grow bacteria. A lot of people are saying 140 degrees. There actually isn't a temperature specification, and it just says at a temperature. Do you have any concerns in the designs you're showing, and how do you handle that, keeping the water at a temperature to prevent bacteria?
Sure. We have not had any issues with it, but I certainly understand the question and the reasoning behind the question. One of the things you could do with these auxiliary water heaters, whether they're a tankless electric or a tank type, you could certainly put that temperature thermostat to 140. At 140 degrees, you're basically killing Legionella very quickly, I believe in less than a minute. So you could still use this detail for preheating and simply go to another final heating device that's going to raise it to that, let's say 140 degree temperature, and definitely put that thermal mixing valve on the the outlet, because you do not want to send 140-degree water off to your fixtures. You definitely want to temper it back down again. So yeah, you could still use the same detail. You're not going to be able to get most heat pumps up into that temperature range. There are some that can do that, some water-to-water heat pumps. I don't know of any air-to-water at this point that could really do 140-degree domestic water for you. And if you did have one, the COPs would not be very good. So keep the heat pump on the preheat function, top it off to whatever temperature you're comfortable with, and put that thermal mixing valve on and make sure you don't scald somebody. Okay.
So I just want to point out there are a bunch of questions we haven't answered, but we will answer all of you towards the end. Just wanted to throw that out so nobody thinks we're ignoring these other questions. So.
Yep. Okay, so put yourself, you're the designer, all right, and you're going to get one of these, is it better to, multiple choice questions here, okay, and you're the designer. Now, we've talked about the fact that the COPs of heat pump go down as the water temperature you're asking it to produce goes up, okay? We also talked about the fact that the lower the temperature of the buffer tank, the less preheating you're getting. So where's the sweet spot? Should I go to a certain temperature where the COP of the heat pump stays fairly high and then take the rest of the temperature rise with my auxiliary heat? Should I use outdoor reset control to control the buffer tank? Should I just completely separate the domestic hot water load? So here's one choice. Let's say we're going to maintain a buffer tank, relatively high temperature, such as between 100 and 110, and get a pretty high percentage of domestic water preheating. Now, the percentage you get is pretty much just proportional to the difference between your cold water temperature and the temperature requirement leaving the overall system going to your fixtures, okay? So if we're taking 45 or 50 degree Fahrenheit water up to, let's say, 110, and we're only asking our system to produce 120 degree water, we're getting a high percentage, whatever that ratio of temperature differences would be. If we're only taking that water up to, say, 80 degrees, obviously we have a lower percentage. So choice number two, well, we're going to use outdoor reset control to turn the heat pump on and off, and the buffer tank temperature is going to be just warm enough to meet our space heating requirement, and we're going to take less preheating on domestic hot water. And the other choice would be, let's completely separate the domestic hot water load. All right, we'll eliminate that heat exchanger we talked about, the flow switch and so forth. We're just going to use a separate, let's say, an electric tank type water heater. So what I did is I set up the spreadsheet models again, and we assumed our domestic water load here was 60 gallons a day heated from 50 to 120 Fahrenheit. So we ran the spreadsheet for several different buffer tank temperatures. You can see those. These are the average temperatures in the buffer tank. So for example, if we turn on at 100 and we turn off at 110, our average is 105 right here on the graph. Now, the blue line up above here and the data points on it, that's space heating only. Okay, that's where we're not assuming we're extracting any energy from the buffer tank for domestic water, just for space heating. The red line is when we have both space heating and domestic hot water. Now, if we could average our buffer tank at 120 degrees, you see those 2 points are pretty close together. We're still taking a little more energy out of the system with domestic water, so the red point is a little lower than the blue point. But look at what happens as we go to lower buffer tank temperatures. You can see that our seasonal average coefficient of performance is going down, and that makes sense because the cooler the buffer tank, the less domestic water preheating effect we're getting from it. Okay, so if we could if we could average 90 degrees in our buffer tank, we're at about what, maybe 2.8, 2.9 seasonal COP with a combination of space heating and domestic. But look at where we are if we're just doing space heating. We were up there at like 3.4 roughly. Now, we ran we ran the spreadsheet, and here's what we assumed: full outdoor reset control of the buffer tank temperature, and then any supplemental heating for domestic water was provided by electric resistance heating, either as a tankless water heater or as the element in a tank type water heater. And again, this was run for upstate New York, Syracuse, New York weather data. And we averaged a COP of about 2.8 under that condition. And then we ran it again, and we completely removed any all energy for domestic water heating was coming from electric resistance heating. 100% of domestic water was from electric resistance heating. The buffer tank was being maintained based on outdoor reset control. And you can see our COP drops roughly 2.6, 2.5. And the reason is that 11% of that total energy, and by total energy, I mean total space heating energy plus total domestic hot water heating energy. 11% of that total was being supplied by an electric heating element at a COP of 1. Okay, so the sweet spot seems to be right here, where we're using outdoor reset control on the tank temperature. So we're benefiting from reduced tank temperatures under those swing season and partial load conditions. And we're using some type of supplemental device to heat our domestic water to the required temperature. Now, of course, these numbers are case specific. We changed the location, we changed the heat pump performance, we changed the load. You really do need to have a spreadsheet or other computer simulation to do this, because there's a lot of things that are changing simultaneously here. But think of it in practical terms. The total energy that you send for space heating in most houses today is significantly more than the energy for domestic water heating. So you tend to want to create conditions that favor good performance in space heating, even though they also require supplemental heat input for domestic hot water. Okay. Now, just a few details, and then we're going to jump to some questions. Now, we've looked at the basic idea of this system already, but I just want to talk about some of the advantages of it. And you see some of the bullet points over here. One of the nice things I like about this is we're using a single tank in the system. We aren't using one tank for buffering space heating load and another tank for domestic hot water. We're leveraging the thermal mass in that buffer tank, and that gives us stability in domestic water heating. There's a lot of energy stored in that tank, and as long as that circulator runs, we're connecting that heat exchanger to all that thermal mass in the tank. Brace plate heat exchangers, they respond very quickly. They have a very high ratio of surface area to internal volume. If you've worked with these, you realize literally within 1 or 2 seconds, these things can be at essentially very close to a steady state condition. The other thing I like about this approach, that heat exchanger is fully serviceable. When you have a tank that has an internal coil, you may get years of service out of that, or if you happen to have, very aggressive water and you don't treat that water, if you do have a pinhole leak develop on an internal coil, obviously that tank has got to be replaced, and that's expensive and it's burdensome to do that. When you have an external heat exchanger, you can basically disconnect the piping. You could have unions on it, take it off and replace it much faster than you could deal with replacing a tank, and for much lower performance or cost. Now, the other thing that's nice about the external heat exchanger, you have forced convection on both sides of the heat exchanger. With an internal coil, you have forced convection through the coil because something is pushing the water through it, but you have natural convection between the tank water and the outer surface of that coil. And natural convection is a weaker, substantially weaker process than forced convection. With a brace plate heat exchanger, the circulator is forcing the convection on the primary side, and of course, the flow of water driven by the building pressure through the secondary side also creates forced convection. So you have very predictable performance. You can go to software. I'll show you an example of some software that I've used in the past, and you can model these conditions and select a heat exchanger. Another nice thing about this, you're storing very little heated domestic water. Remember, the water in this tank is system water. So from the standpoint of Legionella, we have very little volume of stored water. That heat exchanger literally might contain less than half a gallon of domestic water, okay? And the other thing is, oftentimes people, when we talk about this, well, yeah, but you're running this circulator every time you need domestic water. Well, we've done the math on that, and it actually works out to literally less than 5 cents a day. It's almost trivial the amount of electricity that circulator uses. This is a small circulator. If it's an ECM circulator, it probably maxes out at under 50 watts when it's running. And remember, that's only running when that flow switch is closed. So it's running several minutes a day, but 50 watts for several minutes a day, even at 20 cents a kilowatt hour, is it's pennies a day to run that circulator. So that really adds very little to that operating cost. Okay. Now, I want to stress the importance of that check valve, either built into the circulator or an external check valve here. Make sure that when we have flow coming back from our heating distribution system, we don't go up through the heat exchanger in reverse and go and short circuit the tank. You can also put a check valve down here. What this does is it just prevents heat migration backwards into the space heating circuits. If you're using this in the summer, for example, if you're maintaining that buffer tank with the heat pump in the summer, this just prevents heat migration farther back into the system. Here's just an example. This is a little 12 kW system. Okay, and you can see this is pretty small just compared to the mechanical pencil here. Inside there, you've got a contactor. You can see some pretty heavy wiring here. These use a device called a triac, and a triac is basically a solid state switching device, and the triac is controlling the amperage that is going into the heating element, which is in this polymer enclosure back here. This is an engineered polymer enclosure. There are safety switches. You see, this is a I call these clicks-on switches. It's a small snap switch that would open usually at about 140 degrees. These will pop open just if there was a failure of the primary controller on this. That's your protection against very high temperature water. You bring your line voltage wiring in down here. Here's cold in, cold or hot out. It's a pretty simple device. All right. This does have a flow switch built into it. And I want to show you there's the detail that you can use on some of these where you actually can use the flow switch that's built into the tankless water heater to turn on that circulator we talked about rather than buy a separate flow switch. Now, if you are using a tankless electric water heater, I do want to caution you, these draw a lot of current. Okay, and there's no way around it. It's Ohm's law here. So if you want to look at a typical single phase 240 volt system, the amperage is simply the kW, the kilowatts that the heating element is going to operate at full power divided by 0.24. Okay, I would recommend nothing less than a 200 amp service entrance for something like this, especially if you're going to a large one. This is what I call a whole house system, okay? And this actually requires two 50 amp double pole breakers. All right, there's again, you do the calculations, you figure out what's necessary. Remember, these are designed, the intended purpose of these is to take cold water and bring it right up to the required water temperature in a single pass. So it takes a lot of instantaneous power input to do that. So if you're going into a retrofit situation, an older house, it might have a 100 amp service entrance, probably not the best approach here. You probably would be better served by going to a tank type water heater with a lower kW requirement on it. as opposed to one of the tankless units. Okay, heat exchangers, you can get them in a lot of different sizes. Again, I want to caution you, don't go with these little heat exchangers. 3x5, 10 plates deep is not going to give you much preheating effect. It simply doesn't have enough area. In general, you're looking at probably a 5x12, which seems to be a fairly typical size from several different manufacturers. You can get some tall ones like this, 3x20s. The software that I'll show you in a minute, again, will let you experiment with different geometries on the heat exchanger and see which one meets your requirement, okay? So they're widely available. You can get these in both 316 stainless and 304 stainless, okay? I mentioned very high surface area to volume ratio, so they respond very quickly. Typically within 1 or 2 seconds, you're near steady state. So the overall response time, flow switch, circulator, heat exchanger, under 5 seconds. And I would challenge you with a gas-fired water heater, a gas-fired tankless water heater from a cold start, you're upwards of 30 seconds before you're actually delivering hot water from that. You simply have a lot more warm up to do. You've got to ignite it, prove ignition, operate the valve, warm up the heat exchanger, and so forth. So nice in terms of fast response. Okay, now up to another poll question here. And since we've been talking about these stainless steel brace plate heat exchangers, the poll question, how often do you use a stainless steel brace plate heat exchanger for domestic water heating? And Mike, I'm gonna have you watch those numbers. Again, I suspect, because the detail we've talked about here is not widely used at this point in North America, that the majority of you probably are not using it.
Yeah, my feeling's the same, John. It's the fun part of the poll. We get to find out what are people doing. So we got 50% people voted. We'll give it another minute.
Okay, and while those are coming in, keep in mind the details we're showing you here, just like last week, we showed you some, what I'd call some unconventional details for things like bringing the earth loop piping through a concrete basement wall. Keep an open mind on this. Sometimes the standard details that we get used to, and certainly in domestic water heating, the standard detail would be an indirect tank heated by a boiler. But as we move into more and more usage of heat pumps, some of these new details which we're exposing you to may be appropriate.
So the results are in. So 11% of people are using a plate heat exchanger. 42% are seldom. 6% are only if the indirect is not big enough, and 40% is never. So it's a pretty good variety there.
Yeah, and actually that the first choice there, 11% in most systems, is actually, that's encouraging. And again, folks, I'm not saying that you're wrong to not use this. I'm simply saying that there are advantages, there are benefits of looking into an external heat exchanger. One benefit, and it's a different system, but if you can't find an indirect water heater that could handle, let's say, 1 million BTUs per hour of heat input, you can go to an external heat exchanger. So even though we're talking about relatively small residential applications here, you may have a commercial application where you have a very high potential demand for domestic hot water, and you simply can't find an indirect that can handle that. You can go to a larger brace plate heat exchanger and basically build up that heat transfer capacity that you need. Okay. Now, several of the heat exchanger manufacturers have freely available online software. This is one from what used to be GEA flat plate. It's now Kelvion. But you can go to this website and you just register and you can have free access. It's cloud-based software. And I did a screen capture just to show you. It's very simple. You have two sides of the heat exchanger, side A and side B. And basically you put in conditions that you want. And the software is intelligent. It knows if you're over specifying the conditions. For example, if the conditions you specify on the primary side would result in a heat transfer rate of, let's say, 100,000 BTUs per hour, but then you go to side B and you specify conditions that would require 150,000 BTUs per hour, the software is going to tell you that. So it will guide you into making selections, and then it'll basically come back with a heat exchanger. Oftentimes it'll come back with multiple heat exchangers that can meet the requirement or are within maybe 30 or 40% over the requirement. So in this particular case, we ended up with a software specifying a 5x12 with 30 plates in it. Okay, and at that point you can go price out that heat exchanger. Again, I would recommend, especially for heat pump applications where where temperature is really a sensitive issue in terms of performance, keep that approach temperature difference no higher than about 5 degrees Fahrenheit. Okay, now one particular manufacturer, and I've checked with them, this was a company called Emax. One of the things that when we first looked at this, we realized there is a flow switch inside this tankless water heater. Could we use that flow switch to not only operate the water heater, but also use it to activate the circulator that brings water from the buffer tank through the primary side, the heat exchanger? So I talked to their engineers about it. And I said, sure. We actually have extra contacts. These happen to be quick connects that are built right onto the coil of the contactor in the tankless water heater. So it would be simple. We would just run a 240 volt circuit to a relay, and that relay would have to be selected with a 240 volt coil. And again, there's a lot of industrial relays that are available. So basically that relay fires whenever the flow switch turns on the contactor in the tankless water heater. And remember, that contactor isn't just opening and shutting, it's closing when the flow switch gets up to some minimum flow. And at that point, the triacs are modulating the current through the element. So the contactor stays on until the flow rate drops below whatever activation threshold the manufacturer has set up. So it's a simple little detail. I would recommend that if you're going to do this, you do verify that you can do this with the manufacturer, because you are actually piggybacking onto the circuitry that they've created. But assuming the manufacturer's okay with it, it's a pretty simple little way. And what this does is it eliminates the need to buy a flow switch. You're basically using the flow switch in the tankless water heater. Now, if you're using a tank type water heater, obviously it doesn't have a flow switch. You're going to need that external flow switch. Last detail I want to show you. Excuse me. This is a detail that uses this concept of an external heat exchanger along with a recirculation system and a thermal disinfection detail. So we'll start out, we've got a thermal storage tank or a buffer tank here, and something is heating that. It could be solar collectors, it could be a heat pump, it could be a boiler, it could be a combination of heat sources, okay? And perhaps we're taking a space heating load off of it. Over here, we've got our braze plate heat exchanger with a circulator. And in this application, this high efficiency circulator, I would use an ECM here. I would just run it whenever there's a potential for domestic hot water demand in the building. So perhaps you turn it on at whatever, 6 o'clock in the morning and you run it to 10 o'clock at night. You could turn it off at night, okay? But the idea is that we're maintaining a temperature based on whatever tank temperature we have. We're maintaining the primary side of the heat exchanger pretty close to that temperature. And then we have a recirculation loop over here. Okay, so we have our preheated water going out, and you'll see I've got a series of smaller electric tankless water heaters here. These might be 3 to 5 kW units, under sink units. So maybe here we have a bathroom group, we have a lavatory, we have a shower, maybe we have another one in the kitchen, maybe we have another bathroom group over here. And these draw from our recirculated preheating line. And notice that the gray that you see here is insulation. It's a recirc loop. We want to make sure we insulate it. And they simply top off the temperature to whatever they're set for. You could set the bathroom group potentially at a different temperature from the kitchen group. Okay, so, and we're also showing a pressure relief valve, flushing valve, so we can isolate and clean each of these if necessary, and a ASSE mixing valve to make sure we don't scald anybody. This point of use mixing valve, a 1070. Okay, now we have a small stainless steel circulator that does the recirculations. Our cold water enters here. We have a check valve to make sure we don't go backwards on our recirc. All right, we have flushing valves set up for the secondary side of our brace plate heat exchanger. And way over on the far right, let me just move my control panel here for a minute. Here we go. Way over, oops, go back. Over on the far right, I've got a dedicated tankless water heater, and the function of this is strictly to provide a sterilization cycle, thermal sterilization. Thermal sterilization is becoming more common in commercial domestic water recirc systems. The basic idea is we're going to take the loop temperature up to a point that's going to kill Legionella within minutes. So let's say we take that loop temperature up to 140 degrees. We maintain it for easily killing everything within 30 minutes at that temperature. Okay. Now, it doesn't take a lot of energy to do that because remember, we're not heating domestic water with this. This is strictly making up heat so we can get the recirc loop up to, let's say, 140 degrees. And we're sterilizing. We're basically heating any domestic water short of these short runs that go up to these tankless water heaters. We're heating our recirc loop and our secondary side of the heat exchanger, and we're doing a thermal sterilization. And then basically we have a three-way valve here. During thermal sterilization, the flow would go through this water heater, come around the loop, okay? Our recirc pump is providing the propulsion of the water there. And then once our thermal sterilization cycle is over, our mixing valve, or I'm sorry, our diverter valve just goes back to recirculation. So this puts a lot of these concepts together. And the other nice thing about this is your recirculation loop, other than during thermal sterilization, is running at a lower temperature. It's only running at roughly the temperature that's in your buffer tank. So your line losses, your thermal losses through your insulated pipe are going to be lower because of that, okay? So that's kind of taking this concept and expanding it into multiple point of use tankless water heaters. And we're going to go to questions in just a minute, but before we do that, next week, November 2nd, we're going to talk about buffer tank piping options. And just a prelude, there's several different ways that you can pipe buffer tanks. What we call 4-pipe configuration down here, 2-pipe, and 3-pipe. All right, you might be wondering, well, you know, which one should I use in what application? Which one is better? We're going to get into that next week. So, Mike, if we've got a few questions, I can stop here and then we can move on to the find effects after a couple questions.
Yeah, no, that sounds good. So I'll just jump through a bunch of the questions here. Daniel actually has a really good one. Where is the trade-off in terms of cost, performance, or on the indirect versus the superheater? From a cost of purchasing standpoint, you know, an indirect is going to cost you as a contractor, let's say $1,000. A superheater is going to cost you $500. The superheater will passively produce 50% of your domestic hot water use for a small family. The challenge is that's annually. That's not hey, every day you have 50% of your domestic hot water. John, right. What do you consider the trade-offs in terms of cost and performance?
I've actually not run calculations on that. It's going to be case specific. It's certainly going to depend on the water load. I would tell you the greater the water load in the building, the lower that tank temperature is going to be and the better the performance of the de-superheater is going to be. I would tell you that people that are going to use their heat pumps more for cooling if you're in a warmer climate and you have a higher cooling load, or if you just prefer a lower temperature during cooling season. The more you run that heat pump in cooling, the more free domestic water heating you're getting. So it would probably take another spreadsheet model to actually know the exact numbers there. And certainly the cost of energy is going to be a factor too. The cost of energy, if it's electrical energy going through a heat pump at a COP of, pick a number. In the summer, the COPs are going to be pretty good. It's a complex question. It's a good question, and it's a proper question. I don't have a number to say, you're going to get a payback in 5 years or 10 years, but certainly the trending, if you look at energy price trending going up, if you look at, electrification coming in, my gut feeling, is, but put the money into the de-superheater at this point. It's worth it. I think if you, in a residential application, if you're buying that heat pump strictly for, maybe floor heating in a auto service garage, you have minimal domestic water load. Obviously, it probably doesn't pay to get the de-superheater. So it's very case specific. Residentially, I would probably say that you will have a positive return on your investment if $400 or $500 extra for the de-superheater over the life of that heat pump is going to return itself several times over.
Perfect. Jeff asked a really good question. So he's going back to our Turbomax discussion and wants to know if we need to worry about the ability of the tank to absorb the load of the heat pump. I'll just caution on the indirect component of this, which is not what Jeff is referring to. You have to be very careful on a air to water or water to water heat pump to make sure that that energy has some place to go. If you drive the inlet water temperature of that unit up to 120 because you can't dissipate it, you can cause catastrophic failure to that unit. So you have to be very cautious of that. John, do you have any concerns with the Turbomax or similar tanks and absorbing the load of the heat pump?
Yeah, I would echo what you're saying. You do not want to create what I call the heat transfer bottleneck. And the classic bottleneck that could set up here is a indirect tank with a very small coil in it. If you buy a standard indirect and it has a coil with maybe 5 or 6, rotations of the coil inside the tank, remember those tanks were not designed around the concept of low water temperatures in the coil. They were designed around scalding hot water temperatures in the coil, 180 to 200 degrees. If you look at the ratings, that's what you'll find. You'll find water temperature assumptions in the coil of 180 and 200 degrees Fahrenheit. If you simply take that tank and attach it to the heat pump, what Mike was saying, hopefully the heat pump will have a safety. Most of them do. They have a high pressure switch on the condenser. And what's going to happen is the heat pump's going to turn on. And again, let's say the heat pump's producing 40,000 BTUs per hour, but that little coil in the bottom of that indirect is only dissipating 25,000 BTUs per hour. All right, so you're producing 15,000 BTUs per hour more than you're dissipating, and you only have maybe 5 gallons of water between that heat pump and that coil. That water temperature is going to climb up very quickly, and hopefully the heat pump will shut itself down based on a safety. And when it does that, it's probably going to lock out. It doesn't just automatically restart because the heat pump understands there's something there that is not accepting the heat as fast as the heat pump is producing it. So the manufacturers set up those safeties so that they lock the heat pump out. You have to go down and basically either turn the breaker off and reset that system because the same thing's going to happen, by the way. Even if it automatically reset, it's just going to repeat that. It's going to constantly short cycle. So again, the big caution is if you're using a standard indirect with any type of hydronic heat pump, water to water or air to water, make sure that the tank can accept the heat as fast as the heat pump can put it out. I've seen this happen, and it's going to be what unfortunately I'll call, it's going to be a common situation for people that simply don't understand this or don't adhere to it. So the bigger that heat exchanger, the better. If you can't find an indirect that can handle that, use an external heat exchanger and size it generously.
Yeah,
Okay.
so Mike has the question, again, going back to your electric tankless heaters, what sort of current draw are you seeing on those appliances?
It's kilowatts divided by 0.24. It's right down to Ohm's law. So take the rated full power kilowatt rating of the tankless water heater, and assuming it's a 240 volt single phase supply, just take kilowatts divided by 0.24, and that'll tell you the amps. They're high. They're high. You're going to be working with minimum probably 50 amp circuit breaker, something. It all depends on the kW. And the manufacturers will tell you what breaker size to put in there. And of course, you're going to be working with larger wire sizes too. A 50 amp breaker, if I remember right, is a number 4 conductor, number 4 AWG conductor in aluminum. So.
Yeah, and then we have two comments, just pointing out something that is worth pointing out. The discussion we're having here will vary depending on what jurisdiction you're in. So the Ontario Building Code will actually penalize you for using electric heat, and in some of the other areas, it's the same. So you obviously want to be aware of what you are and are not allowed to do. If you're in Ontario and you're unsure, you can certainly call or email us directly, and we can put you in touch with our outside sales engineer who can, help you a little bit from the standpoint of what you can and cannot do in Ontario.
Would you be penalized in Ontario for an electric heat pump versus electric resistance heating?
Yeah, well, you're seeing the government is making a push for heat pump technology for a whole variety of reasons. That's the reason that you see Enbridge and all of the major builders pushing aggressively into it. That's one of the studies that's attached as a handout that everybody can download. So certainly heat pumps and the electrification of Ontario and Canada, for that matter, is high on the agenda for our government right now.
Yeah, so the penalty would be for electric resistance space heating, I'm assuming.
Yeah, nobody in Ontario is going to be eager to jump into the let's do electric heat for a house. When you're talking 15 to 20 cents a kilowatt, if you get up north into northern Ontario and you have what's called a seasonal home, i.e. the government knows you don't live there all the time, you'll actually pay a higher tax rate by a significant factor just because it's electricity rate, just based on the fact that it's a seasonal home. So.
Yep.
Yeah, heat pumps are a good idea. Just straight electric heat, probably not the route you want to be going anywhere. Another question was, John, what standard do you use for calculating the amount of hot water needed?
I ask people, but a nominal number is for an average family is about 15 gallons per day per person is typically where I'll start. Now, if somebody tells me, I've got 3 daughters in the house, they take showers in the morning, they take showers at night. If it's a high domestic hot water usage, you've just got to ask people to get an idea. I suppose if you really want to pin the number down, you might be able to get some type of a flow meter that records it. But I would say 15 gallons per person per day is a reasonable number. High water usage may be going up to 20 gallons per person per day. Obviously, when you're engaging a client, you have to come up with a load that is mutually agreeable. So, we would talk to people and they'd say, well, we're average people in terms of our water usage. We have the 2 gallon per minute shower heads. We don't waste water. We do maybe 2 or 3 loads of laundry a week. If it's an average situation, 15 gallons per day per person, and I would put that right in the design agreement. This is what we're designing around based on our discussions, and make sure the client in a sense, signs off on that. We're designing around, let's say, family of 4, 60 gallons a day heated from whatever typical groundwater temperature would be up to, again, a mutually agreeable number. If you're going to go to 140 and you're not, you definitely are going to be mixing down from a safety standpoint. What that final delivery temperature is, if you agree on, I suggest 120 degrees Fahrenheit. That's, keep in mind, you cannot take a shower at 120 degrees Fahrenheit. You will get burned. Average shower temperature is probably between about 101 and 105 degrees Fahrenheit. So, it's got to be a mutually agreeable number, but a starting point for an average family, 15 gallons per day per person.
And then Daniel would like to know, is there any different configurations that you would do for hot water recirculation?
Well, yeah, there are, like in a commercial application, oftentimes the recirculation loop has multiple branches to it as opposed to just a single loop that's common in residential. There are some special valves that are out there now when you do have multiple uh, branches in your recirculation. And just imagine, for example, a hotel with maybe 3 different wings to it, and you have a separate branch that goes out to each of these wings, and ultimately they come back together. You can actually buy valves today that will sense when there's domestic water usage, and they will actually throttle back on the amount of recirculation flow that's going through there. So the way they do that is with temperature. If the valves are on the return side of the domestic recirc loop and they start feeling warm temperature, they can actually throttle the flow down. Now, in a commercial application, the advantage of that is you can use a variable speed pump on the recirculation system, just like a variable speed pump with thermostatic valves on radiators. And in a commercial application, again, imagine a large hotel, 200 or 300 rooms. You could have a pretty sizable recirc pump, and that pump can throttle back based on the actual recirc requirement moment by moment. I would always recommend insulating your recirculation lines. Actually, one of the hydronics issues from Calefi gets into all the sizing procedures, the calculations. If you look at, let me just see which issue that is here, just as a reference. I think it's 21 and 22, issues 21 and 22 of hydronics. Has the calculation procedures for sizing up a recirc line. And just one last point before I leave that, remember that when you're looking at sizing that recirculation line, you're only looking at enough flow to maintain a temperature drop, maybe 5 to 10 degrees Fahrenheit in that recirculation line. Recirc pumps don't have to be very large, especially residential applications.
Okay, perfect. Jeff has a good question in relation to the buffer tank with a heat exchanger for domestic. You're maintaining that buffer tank in the summer is his question.
Yeah, that is a good question. And yes, I'll tell you the ideal scenario, and we do have some slides coming up in some of the later webinars on this. The ideal scenario, if you're working with an air to water unit, is with an inverter compressor. One of the nice things that you can do is you can set up controls that can maintain that buffer tank at a warm temperature in the summer. So you do have your domestic water 12 months a year. And if it's in the cooling mode operation, there's a couple things you can do. If you have an inverter compressor, a variable speed heat pump, you can go directly to an air handler without going through the buffer tank. The heat pump will actually modulate the speed of the compressor to maintain, let's say, 45 degree Fahrenheit chill water temperature to that air handler. Now, you might say, well, what happens if I'm calling for cooling and the tank temperature starts to drop? You've got to prioritize control configuration. Basically, when the tank temperature drops, you would temporarily leave the cooling mode. you would have a motorized diverting valve that simply directs the water coming out of the heat pump. Instead of going to the air handler for cooling, it goes back to the tank, and it would operate the heat pump for a few minutes, bring the tank temperature back up. Keep in mind, in the summer, you've got high ambient temperatures. That heat pump is really going to be at high capacity and high COP. It's not going to run very long to bring even a 119-gallon tank up, 15 to 20 degrees. It might run 5 minutes. And at that point, you would go back to cooling mode operation. The diverter valve would change back. So yeah, you can definitely set systems up to maintain that buffer tank in the summer. Now, if you're using the buffer tank for chilled water in the summer, essentially you would just shut off the preheating function. You're not going to get preheating function for that. You could just have a switch in your control system that would just disable that during the summer. But again, as more and more heat pumps move towards inverter compressors where you have variable capacity, this lets you use a single buffer tank, maintain it at a heated condition 12 months a year, and still be able to do chilled water cooling.
Perfect. So Chris makes the comment, with electric on-demand heaters, are there situations where the combination of domestic flow and the temperature rise is too low to activate that heater or cause the on-demand unit to cycle on and off too frequently?
You can, yeah. Basically, the flow switch, if you look up the specs on the flow switch, the smaller flow switches get down to around an activation flow of about 0.7. So yes, if you just open a faucet and have a trickle of water coming out, it's not going to activate that circulator, or the flow switch contacts are not going to close. But what I found is that most lavatories, certainly any shower or bathtub draw, is usually going to go over 0.7. So yeah, if for some reason you anticipate very, very small draws on domestic water, very low flow rates, I suppose one of the things you could look at doing is simply to take a low power circulator and run it whenever domestic hot water might be drawn. In other words, let's say we turn a small 40-watt circulator on that's moving hot water from the top of the buffer tank through the primary side of the heat exchanger. You could turn it on at 6 in the morning and let it run all day and shut it off at, say, 10 o'clock at night, or whatever times you want. That would maintain that heat exchanger warm at all times. So even a small trickle of domestic hot water has got to draw cold water through the heat exchanger under that condition. But as I say, in most cases, any kind of a shower tub draw is going to turn that on. If you just turn on a faucet at a very low flow rate, it simply won't activate the preheat, which, you don't get the benefit of the preheat, but down the line, you've got either the tankless water heater or you've got the, a small tank type water heater, which will take care of that for you.
Okay. And then Daniel asks, how often would you recommend running the sterilization cycle?
There's some numbers on that. Let me just see. I'm looking at a reference right next to me here that probably has those numbers. At 140 degrees, Legionella will be killed. Let's see. Legionella die within 32 minutes at 140 degrees. If you go up to 158, which is 70 degrees C, let's see, killing Legionella, I think literally within almost instantaneously at that point. So I would suggest around 30 minutes, maybe 40 minutes at 140 degrees should be adequate once a day to kill the Legionella. You could go to a higher temperature and do it more often, I suppose. And I should point out in that configuration too, it's very important. In fact, let me go back to that slide. You notice that during thermal sterilization, your recirc loops is hot. It could be 140, it could be 160, but you have an anti-scald valve on each one of those tankless water heaters. So the water that's going to get to your fixtures, even if the recirc loop was at 160 degrees Fahrenheit, is only going to be as hot as the setting on that valve. Make sure you put those valves in there.
So John, leave this slide up because it'll fit well into Daniel's question. So Daniel's asking, with the setup with multiple small electric top-off units, is there a tolerable reduction of domestic hot water wait time that we may not need a recirc?
Well, yeah, but you know, it's going to be less. I mean, I guess I'd look at it this way. If you don't have the recirc, you're going to be drawing cold water from wherever. Yeah, it's going to come up to temperature. You're simply going to use more energy to do it. So the wait time should be short because assuming you've sized if you've sized the tankless water heater to go from your cold water temperature, 45, 50 degrees Fahrenheit, right up to your delivery temperature, if you've sized it for that, the wait time should be very short. You're not taking advantage of the preheat coming from your thermal storage tank. And, the assumption in this is that the energy that heats that water in the recirc loop coming from the thermal storage tank is lower cost energy. It's coming from something other than electric resistance heat, be it a heat pump, solar collectors, biomass boiler. You're trying to get as much of your total domestic water lift coming from your cheaper energy, and then only use the more expensive electric resistance energy to top that temperature off. So it's not really, I agree with Daniel, the wait time could be very short in either case. It's a matter of what's the mix of energy and the cost of that energy.
Perfect. So Mike just wants some guidance from you on sizing a tankless electric heater. Do you have any tips or suggestions on how to do it properly?
Yep. I would go right to the manufacturer. They typically have got the guidance in there. The trade-off that you run into with a tankless is basically the temperature rise versus the flow rate going through it. Once that tankless is activated, once you reach that minimum flow rate to activate it, the temperature rise and the flow going through there, it's a trade-off. As the flow rate going to your load goes up, the temperature rise goes down, because let's say it's a 12 kW unit. Well, 12 kW is 12 kW. It isn't 13 or 50 kW. You only have so much energy input rate. So it's if you look at energy input rate, it's always a trade-off between temperature rise multiplied by flow rate. And those curves are there. And for example, in a average house, you might say, well, maybe I've got 3 bathrooms. Let's assume that 2 of the showers are on simultaneously, and maybe a washing machine is on. So you can get numbers for what those demands are. Let's say my projected worst case flow rate is 5 gallons a minute. All right. And based on the cold water temperature and the set point temperature of the unit, that will lead you to a kW number for sizing. So the manufacturers can size those things up. You basically are going to have to tell them what's my highest expected flow rate and what's my worst case temperature rise scenario. For example, this one, you could look at this a couple ways. You could say, I'm always going to have some preheated water in my recirc loop. So what's the minimum temperature going to be? Is it 80 or 90 degrees? If that's the case, that means a lower temperature rise and potentially a smaller kW unit will provide that for you. The other way to look at it would be, suppose my preheating function is not working at all. Maybe the heat pump is out of service for whatever reason. And under those cases, my recirc loop is just getting cold water fed into it. In that case, you would size based on starting from your cold water temperature all the way up to your delivery temperature. And that would probably increase the kW. I'm sure it would. It would increase the kW of the unit. Now, the trade-off here is, a larger KW unit is going to cost a little bit more, but again, incremental cost differences here are not really high. Mike, you probably have a better idea, but I would say my guess in the Canadian market for a 12 kW tankless today, Canadian dollars, maybe $300 to $400, something like that.
Well, I'll refer you back to the poll where 60% of people said they don't do it. I'm one of the 60%. So we probably do maybe a dozen electric tankless setups a year. Yeah, I'm not sure if that number would be right. It's probably close, John.
Yeah. I mean, go online. You can find some representative numbers there.
Tim's got an interesting comment. So he's wanting to know if you've ever experimented with the HeatWorks electric heaters that have graphite plates that purportedly have a much higher efficiency. What are your thoughts on that?
I have not experimented with different types. I know there are different types of heating elements out there, and I know that the graphite is one of those. Essentially, it comes down to this: electric resistance heat is a COP of 1, no matter how you take that electricity and turn it into heat, whether it's through graphite or whether it's through some other material. So, perhaps one material over another has an advantage from the standpoint of response time or longevity, but from the standpoint, a pure thermodynamic standpoint, 1 kilowatt is 3,413 BTUs per hour, and there's no material that can take 1 kilowatt hour and turn it into more than 3,413 BTUs per hour. So, I have not experimented with different materials. I know there are several manufacturers that are offering electric tankless water heaters now, and they do use different elements. Again, I don't have background to say, definitely use one over the other.
Okay. Yeah, interestingly, Dave is pointing out that Emax, which I think is one of the ones we were talking about here, John, is he's saying it's actually not designed to allow for preheated water to enter them.
I'm not sure if that's a particular model or not, but most of them have thermostatic controls. They're being applied in situations where, preheated water, whether it's coming from a heat pump or a solar collector or whatever. I don't know. There may be some that don't have that capability, but I would look for one that does have the ability to take preheated water, and I'm sure there are products on the market that can do that.
Okay. And then we also have a question. This one comes up a lot. It's one of my favorites. So if I have a plate heat exchanger that has a 1-inch connection on it and I run 3/4 inch pipe to it, is that going to impact the capacity of the heat exchanger?
No. It's the heat exchanger is strictly gallons per minute. However, that gallons per minute gets there, it doesn't matter. You will find, for example, the project we did with the 5x12x40 plate, that actually comes through with 1.25 inch male pipe thread on all 4 connections. So we were piping the primary side up with 1-inch pipe. So we're buying 1.25 inch female down to 1-inch sweat adapters. They're expensive. Any type of adapter fitting like that. But no, you do not have to worry about that. We actually have the 3/4 inch pipe on the domestic side of that heat exchanger, transitioning to 1.25 inch going into the heat exchanger itself. It's not a problem.
Jeff has a good one that we may have to address with a schematic later, but I'll see if you want to verbally describe this one. So here in Ontario, drain water heat recovery is required by code. And Jeff is curious to know how you would integrate this into the system. Hence my volunteer to maybe do a drawing on it.
Yeah, I would integrate drain water heat recovery upstream of this braze plate heat exchanger. You might be taking 45-degree water to, I'm making a guess here, 55 or 60 degrees, depending on the drain water heat exchanger. And of course, remember that is only active when there's actually water going down the drain. But yeah, I would simply bring your coldest water to the drain water heat exchanger, go through it, and then head over to the cold water inlet on the braze plate heat exchanger or on these tanks that we've talked about.
Perfect. Alan's got a question. He wants to know how well does this approach work with solar thermal preheating instead of a heat pump?
Sure, absolutely. It should work great. In fact, I would say the potential on a solar system would be even higher because you can get the thermal storage tank at pretty high temperatures with solar thermal. Think 170, 180 on some days in that tank. So you're going to get really hot water going through that braze plate heat exchanger, and the water coming out the other side is going to be scalding hot domestic water. So the caution would be, again, make sure you're using that anti-scald thermostatic mixing valve. But I see absolutely no reason why it wouldn't work as good, if not even better, with a solar thermal system compared to a heat pump. Or for that matter, a biomass boiler. If any of you are doing cordwood gasification or pellet boilers, you could be using this with some type of heat recovery in an industrial situation. You could use this with a micro cogen system. Anything that has a thermal storage tank associated with it is a potential application for this.
Perfect. And then one more question, John, then we'll move on to the remaining slides. This one's from Chris. He just wants to know if the tankless electric units are modulating and what range of modulation.
Yeah, most of them are modulating because they're using a solid state device, a triac. And in theory, a triac can modulate from 0 to 100% of the current. What you have going on in these is a small circuit board, and the temperature information is coming to that circuit board, and the circuit board is controlling what's called the gate on the triac. So it's sort of like a transistor. When you control the gate current into a triac, what the triac does is it takes the modulation in the gate current, which is relatively low current, and it creates the same modulation in a much higher current going through the heating element. So if we bring the gate current from 10% to 50%, we're going to get from 10% to 50% of what might be 50 amps or 60 amps going through that heating element. So yes, most of them. I should backtrack. In the old days, going back 40 years ago, when tankless electric water heaters first hit the market, they did not modulate. The flow switch turned them on and they were just bang on, bang off. They were full power or no power. Today, most of them do modulate. And that's really what's made the difference between the ability to accept preheated domestic hot water. So, if you're coming in at 100 and you're trying to go out at 110, obviously you don't have to put full power on the unit. Okay, so let's go on. Again, I want to thank the sponsors that have worked with us. Again, Eden, I love coming up to Eden, and Mike always produces a room full of people, usually 2 days in a row. So we've had a lot of good training sessions face to face, and hopefully someday we'll get back to that. But in this time with the COVID situation, hopefully these webinars that we're doing, from the numbers we're seeing, we're reaching a good size audience, and hopefully you're getting good information. Make sure you download the PDF to get all the slides that I showed you today. And we're going to finish up here. Each one of these, we're going to finish up with a couple, what we call find the fixes. All right. Where's the problem? Why is it a problem? And how do you fix it? So I'm going to start with this one. This was one that anybody that's doing biomass boilers, and I know that's probably not a high percentage of the market, but this could be a case where you might have even a cast iron gas-fired boiler and you're going to some kind of a load that has a high thermal mass to it. And I'm showing a thermal storage tank here, okay? And somebody told you, well, just put a bypass circulator in, a variable speed bypass circulator, and you'll see there's a temperature sensor down here. And the concept or the expectation is that that circulator will speed up if the water temperature entering the boiler is too low. I should say if the water temperature entering the boiler is low enough to cause flue gas condensation. The idea is that that circulator is going to speed up, and it's going to take what you think is hot water from the outlet of the boiler and mix it in right here at this T and get this temperature back up above dew point. Now, if the boiler was always hot, it would work. But let me give you a scenario. Let's say this tank's at room temperature, and we've got maybe 70°F water coming back through here. And let's say our boiler's cranking at full power, okay? And we've sized the flow rate through that boiler for a nominal 20° temperature rise, all right? So we've got 70° water going in. We go through a 20° temperature rise, so we're at 90 degrees out here, all right? I'm going to ask you a question. I need 130 degrees right here to get that boiler above dew point. How do I mix 90° water coming out of the boiler with 70° water coming from the tank and get 130° water right here? If you figure that one out, make sure you patent it, because you're going to be a billionaire. All right, it's thermodynamically impossible to do that. So the point is that this scenario, a variable speed bypass pump, cannot always protect the boiler against flue gas condensation. And the reason it can't do that is it cannot completely uncouple that low temperature load, in this case it's this tank, from the boiler. When you're looking at the subject of boiler protection or anti-condensation control on a boiler, you've got to have a hardware combination that can decouple when necessary between the boiler and that thermal storage tank, okay? So regardless of how fast this bypass circulator is running, you know, even if it was running at 100 gallons a minute, 100 gallons a minute of 90°, well, it wouldn't be 90° water at that point, because you'd be blasting the water through this boiler, you'd probably have a temperature rise of 1 or 2 degrees. There's just no way to get that, the thermodynamics of the mixing where it needs to be to protect it. So a variable speed bypass circulator, or for that matter, a fixed speed bypass circulator, is not a guarantee against flue gas condensation, whether it's gas fired, oil fired, or let's say pellet fired, okay? So, you know, this is just another scenario that somebody conceivably could put together. They could say, well, I'm going to use a three-way thermostatic valve to control temperature out here to this high mass slab. And, you know, within reason, this is okay. And their idea is, I'll protect the boiler by putting this variable speed bypass circulator in here. It's the same scenario. The only difference is, instead of a tank full of cold water, you've got a slab full of cold concrete. It's a very high thermal mass. It's going to quickly pull the temperature in that system well below the dew point of the flue gases. So how do you fix it? Okay. Well, here's one way to fix it, and it actually doesn't use any more hardware. It's just a rearrangement. What we're doing here is we're creating a boiler loop with a fixed speed circulator. So whenever the boiler is active, we got flow going around through here, all right? And we're coupling that to our load with a pair of closely spaced T's. And this is a form of hydraulic separation. So if this pump is off, just about all of this flow will go right straight through these T's and go back to the boiler. All right, so it's sort of like a conveyor belt, all right? And it's at this point, if we don't run this circulator speed up, whatever BTUs the boiler is loading on the conveyor belt are going to stay on the conveyor belt. We're not pulling them off. Well, once our boiler inlet temperature gets up to, let's say, a set point of about 130, we're going to start to ramp up this circulator. And at that point, we're starting to pull BTUs off the conveyor belt and move them to whatever the load is. in this case, it's that thermal storage tank. Now, if this boiler temperature continues to go up, we can continue to speed up this transfer circulator. However, if we start to see this temperature go back down, what that's telling us is that the load is taking BTUs off the conveyor belt faster than the boiler can load them on. And that would send that temperature back down. Well, under that condition, this circulator just slows down. And I've described this in the past as a thermal clutch between an engine and a transmission. So, if you've driven with a clutch, if you let the clutch come out too fast, you will lug down the engine, maybe even stall the engine. You're pulling energy off the engine faster than it is producing energy by burning that fuel. So this is the thermal equivalent of a clutch. And it's a very simple detail. There are products on the market that can do this for you today. And I'm showing what you probably think is a residential application. This could be done in a much larger application. You could have boilers that are multiple millions of BTUs per hour. We're starting to see some of that being done with biomass boilers that are burning either pellets or chips. I think we have a school not far from me that has a 12 million BTU per hour wood chip boiler. And interestingly, they did not do this detail. And when that boiler starts up and in the fall, you can actually see the condensation forming on the backside of the just below the flue gas collectors. Now, eventually the water temperature in the system warms up, but that system has 3,000 gallons of water in underground piping. It takes a while to warm that up. And during that time, that boiler is operating with flue gas condensation. So this detail applied to to a larger system, you might be using it could even be a multi-horsepower circulator. And today, if it's a standard electric motor, you could use a variable frequency drive. If it's an ECM motor, it probably has a 0 to 10 or 4 to 20 milliamp speed control built right into it. It's just a matter of having some kind of a controller that can measure this temperature and then send a voltage to that circulator to control its speed. So that's one detail. Now,
So
number
John,
two. Yep.
John, going back to that slide, Dave has asked the question, what pump to use. I would just point out the pump that I like to use that doesn't require any kind of external control would be the Taco VT pump. So the V2218 has the ability to monitor that return temperature as John's indicating. It's a really cool little pump you can use in a variety of different applications.
Yep. So it's got temperature input built right in, and I do think we're looking down the road here when we talk about the future of hydronics. But I think what you're going to see as ECM motors become more and more common with circulators, you're going to see circulators that have the ability to have multiple temperature sensors connected to them, like the Taco pump does right now. I think we'll see other offerings because by having the ability to read temperature sensors, we can simply put more intelligence into the memory of that circulator and do things like this boiler protection application. Okay, we got one more. It has to do with a multiple boiler system. And this isn't really as much an error as it is an unnecessary amount of piping. The question has come up, do I need to do reverse return piping when I header multiple boilers together and to some kind of hydraulic separation device? Now, that could be a hydraulic separator as it's shown. It could be a buffer tank. It could be a pair of closely spaced T's. And the thinking here would be if I use reverse return, I would have essentially the same hydraulic resistance through each boiler, okay? And you can do this and this will work, but if this is a large system, I mean, that extra piping for the reverse return doesn't come cheap if that's 2-inch or 3-inch copper pipe. So the question is, do I need to do this? And there's two things I want to answer with that. One is, does it matter if one boiler was operating, and I'll put some numbers here. Let's say one boiler is operating at a delta T of 20 degrees another boiler is operating at a delta T of 21 degrees, and the third boiler is operating at a delta T of 22 degrees. You think is that going to have any detrimental effect on the performance of that boiler? And no, it's not. These numbers are going to be pretty close, and even though the flows may not be identical, and therefore the delta T's would not be identical, the difference in performance is probably insignificant. It's probably not even measurable. So that's one. The other response, and I want to jump to the slide to show you this. This is direct return piping. And I want you to notice I've tried to make those headers very large in comparison. Let me go back. Okay, so we've got, let's say, header piping that it might even be the same size as the boiler piping. All right, here we've got much bigger headers. And one of the things I like to use, one of the terms I like to use is what I call short fat headers. Short fat headers are good. All right. The idea here is if we generously size that header piping, the pressure drop along that header is extremely small. And the number to keep in mind, I would size the header so that, assuming all three of these circulators are running and you know what that total flow rate is, size this pipe for no more than 2 feet per second flow velocity. Okay. When you do that, you're going to have very low head loss, very low pressure drop along the header. And I would also keep the headers as short as practical. If you can keep the boilers relatively close together, you might even take these individual pipes from the smaller pipes from each boiler and bring them, if necessary, to a short header location before it goes into the hydraulic separator. So when you have short and generously sized headers that where the flow velocity in the header doesn't exceed 2 feet per second, your head loss is very small, which means the flow rates are going to be very close to each other. It's almost like, in a hypothetical sense, assume the head loss in those headers is 0. If that were the case, it doesn't matter that this boiler is a little bit farther away from the hydraulic separator compared to this boiler. If there's no head loss here, the circulators essentially are just seeing the head loss through the near boiler piping, from here through the boiler and back out to here. So my suggestion to you is generously size the headers, go with a direct return, save the complication and the cost associated with a reverse return header system in a multiple boiler system. And by the way, that same argument would apply to multiple heat pumps, multiple heat sources of any sort that are going into a common header. Keep in mind, short fat headers are good. Okay, I think that's it, unless, do we have any more questions?
No, I think we're good. We've actually answered all of the questions. The only one I didn't answer was where do we get the slides? So the slides will be made available. I will email them out to everybody later in the week. A video of this training will also appear probably the end of next week on our YouTube channel. We obviously appreciate everybody attending. If there's anything we didn't cover that you'd like us to address, you can reach out to me by email and I can help you with that. And anything we think worth talking about, we can also bring up in next week's episode. So November 2nd, November 2nd, we're doing buffer tank piping configurations. Same time, same channel, and we'll make sure we email all the invites out so you guys know how to join us. Any last words, John?
No, I've been watching our numbers, and it looks like we've had good attendance here today. And folks, thanks for tuning in to start your work week with us. Next week, we'll do the same thing, different subject, but we'll try to drill down into that technology. So we'll see you then.
Thanks for attending, guys.